During the aurora nights of May 2024, photos of red skies showed up from places that normally never get them. At the same time, space companies were watching a quieter warning sign. The orbits of low satellites can sag during solar storms. Starlink made that connection mainstream because those bright trains are supposed to be safely above anything like weather. So how can a storm on the sun decide whether a spacecraft stays in orbit? Near Earth, space is not empty. It's the thinnest trace of air, and a solar storm can temporarily make that air puff upward. A satellite doesn't slam into raindrops, but it still feels drag. The same kind of pushback felt when a hand is held out a car window. That car window feeling depends on speed. A low Earth orbit satellite moves around 8,000 meters each second, about 28,000 kilometers per hour. At that speed, even a near vacuum can steal energy. It's not dramatic in a single second, but orbit is a game of tiny losses that add up. Orbit itself is already a weird trick. A satellite stays up by constantly falling. Throw a ball and it drops. Throw it faster and it travels farther before it drops. In orbit, the sideways speed is so high that Earth curves away beneath the falling satellite, and the fall keeps missing the ground. Now for the part that surprises almost everyone. Slowing down makes a satellite fall, and a falling satellite ends up moving faster. When drag steals sideways speed, the satellite drops into a lower orbit. Lower orbits require higher sideways speed, so the satellite speeds up as it descends. Lower also means denser air, which means more drag, which means even more energy loss. A little extra air can turn into a spiral. Earth's atmosphere fades with height. It doesn't end. Hundreds of kilometers up, the air is fantastically thin, but it's still a gas, and gas expands when heated. Warm air takes up more space. In the highest atmosphere, that expansion matters because more space mostly means upward. Heat it, and the whole top of the atmosphere swells, so there are more molecules at the altitudes where satellites fly. A solar storm is the sun throwing extra energy and electrically charged particles toward Earth. Earth has a magnetic field, like a giant invisible bar magnet. Charged particles get guided by that field, and when they crash into the upper atmosphere, they both light it up, auroras, and heat it up. This link was discovered the hard way. In 1859, Richard Carrington saw a sudden bright flash on the sun. Hours later, telegraph lines sparked, compasses swung, and auroras appeared far from the poles. The delay mattered. Light arrives in 8 minutes, but the disturbance came later, hinting that something slower than light was arriving. In the early 1900s, Christian Birkeland built a miniature Earth in a vacuum chamber, a magnetized sphere. When beams of charged particles hit it, glowing rings formed near the magnetic poles. It was a clue that particles plus magnetism could make an aurora, even if nobody yet had a satellite to sample the space between the Sun and Earth. That missing piece arrived in 1957 with Sputnik. Suddenly, the upper atmosphere was measurable without ever sending a thermometer there. Tracking stations timed satellite passes and watched orbits shrink. Engineers expected a fairly steady, nearly negligible drag. Instead, satellites fell faster when the Sun was active. Luigi Giacchia and others turned that annoyance into a tool. If a satellite loses altitude faster, drag must be stronger. Stronger drag means the air up there is denser. So satellite decay became a way to map the density of the highest atmosphere and watch it breathe with the Sun. A quick estimate shows why almost nothing still matters. Imagine a satellite presenting about 10 square meters to the flow. In 1 second, at 8,000 meters per second, it sweeps through 10 times 8,000 cubic meters. 80,000 cubic meters. If the density is around 1/10,000,000th of a kilogram per cubic meter on a quiet day, that volume contains 80,000 times 1/10,000,000th kilograms of air, 8/10,000,000ths of a kilogram, less than a milligram, each second. During a storm, that density can jump several times, and the energy loss that was tolerable becomes a serious drain on orbital altitude. This is why solar storm forecasting is part of modern spaceflight. Solar observatories can watch eruptions leave the Sun. Spacecraft upstream of Earth, such as DSKO-VR, sample the incoming solar wind, the constant stream of charged particles from the Sun, and give tens of minutes of warning. Operators can respond by delaying launches into very low orbits, changing orientation to reduce drag, or using thrusters to climb. In February 2022, SpaceX reported that a geomagnetic storm, a temporary shakeup of Earth's magnetic field, increased drag on newly launched Starlink satellites, and dozens re-entered. It was air resistance as the failure mode, just air that had temporarily expanded into space. As of 2026 Era 106, the open problem isn't whether the upper atmosphere expands, this is settled, but how to predict the exact density spike for a specific altitude and location. The upper atmosphere, often called the thermosphere, ripples with winds and waves. Energy enters near the poles and spreads unevenly. Even weather far below can send tide-like motions upward. Better forecasts will come from combining physics-based models with real-time measurements, precise orbit tracking, onboard accelerometers, and ultraviolet images that reveal temperature and composition. The same chain shows up at other scales because it's one of nature's simplest habits. Heat a gas and it swells. Meteors flare because density rises as they fall, turning collisions into heat. Some exoplanets lose their atmospheres because starlight heats the upper gas until it puffs up and escapes. Near Earth, the expansion is gentler, but the consequences are immediate for anything skimming the top of the air. So those May 2024 auroras weren't just a light show. They were Earth's magnetic shield and atmosphere reacting to the sun. And they were a reminder that low Earth orbit is still inside an atmosphere that can change overnight. As mega-constellations, giant swarms of thousands of satellites like Starlink multiply, the next question is blunt. Can space weather prediction become reliable enough that a bad week on the sun doesn't quietly turn into a bad week for satellites? Like, if this was interesting, hit the subscribe for more and turn that notification bell on.